Welcome to the class. Today we will talk about centrifugal compressor. So centrifugal compressor comes as the first component that we would see for the gas turbine power plant. We know that air enters into the compressor first. So compressor remains the first part. So we have some options for the compressor, and centrifugal of compressor is one such option for that. So we will see what are the advantages and how a centrifugal compression system has evolved. So centrifugal compressor was first used and thought for the aircraft applications. So it was first used after Second World War. Centrifugal compressor was used. Actually, different compressors were thought for the use of gas turbine, and then among that one competition was with axial compressor, and axial compressor was getting developed in Germany, and at the same time centrifugal compressor was developed in Britain. So it was developed by British. So centrifugal compressor and the axial compressor were contemporary, and hence centrifugal compressor was first used in British, American airline, combat airline, this centrifugal compressor actually has some advantages. So we will see what are the advantages of centrifugal compressor. First advantage is it is suitable for low volume flow rate, applications. Second, it is having better resistance. For foreign object damage. Third, it is less susceptible to loss due to deposition on blade. Fourth advantage is it has stage pressure ratio of 4:1. This is a general rough stage pressure ratio with blades of aluminum alloy. This pressure ratio can be stretched to 8:1 with improved blade aerodynamics and materials like titanium alloy. This compressor can operate for wide range of mass flow rates at a given speed. It can couple with axial flow compressor in multi-stage in applications. Centrifugal compressor is used for gas turbine. It is also used for supercharger, in reciprocating engine, natural gas pipelines, and refrigeration plants. We can go up to 5 stages in multi-staging with centrifugal compressor. So this is rough idea about a centrifugal compressor, and as it is told that centrifugal compressor is developed in parallel with the axial flow compressor, and in case of axial flow compressor it was found that it is more suitable for the higher mass flow rate applications. So it is not then developed, centrifugal compressors development is ceased, or it went on a slow pace, since it is not found suitable for higher volume flow rate or mass flow rate applications. But this centrifugal compressor is found very encouraging in case of foreign object damage, in case of low mass flow rate application, in case of higher stage, single stage pressure rise. So these are the advantages of centrifugal compressor. So we will see what are the parts of a centrifugal compressor. So a centrifugal compressor can have multiple intakes, but if we have a single intake kind of centrifugal compressor, then it might have an accelerating nozzle which will accelerate the air, and then it will go towards inlet guide vanes, and after inlet guide vane there will be impeller. So this is general construction of a centrifugal compressor. This shaft is rotating, and in this case we will have this as accelerating nozzle, this is inlet guide van, this is inducer, this is impeller, this is volute, and this is diffuser, this is hub, and this is driving shaft. So these are different parts of a centrifugal compressor. Here for us we will consider this as station I, then for us this station at the entry to the inducer is 1, then at the exit we have 2 for the impeller, and then we have 3 in the volute. So these are the 4 stations for us for discussing the thermodynamic of this centrifugal compressor. Now this impeller is casted on the one side of a disc such that that side of the disc upon rotation will take the air or the gas from the accelerating nozzle and would pass it to the diffuser and then to the volute casing. But it is possible that we will have this impeller casted on 2 sides, and then in such case we have a double sided impeller. In case of a double sided impeller we will have a situation like this where we have one impeller on one side and other impeller on other side of a disc. So this would give us double sided impeller for a 2 side intake. Intake will be from either side for the centrifugal compressor. This centrifugal compressor we can sketch then using thermodynamic relations, but before that let us make one more sketch. Here we will have this is the centrifugal compressor which we are trying to plot on the front side. This is side view and this is the front view of the centrifugal compressor. Here this part is the impeller, this is an impeller, and this we call it as the inducer, and then this would rotate in this direction. Air would come axially to start with, and then air will come axially and then it will move in radial outward direction. Having said this, we can plot thermodynamically the process of compression on HS diagram for the centrifugal compressor. So HS diagram would be, first we are at station I. At station I, this is PI. So if we isentropically compress it, then we would reach P naught I. This is the pressure, but from I station, due to the accelerating nozzle, we will have first decrement in enthalpy. So this is the reach to station 1, this is station I. Then from 1 we would go to station 2 where we would reach pressure P2, and then we would go to station 3 where we would reach pressure P3. So, this is at the exit of the impeller, this is at the exit of the diffuser. But if we would have isentropically compressed, we would have got to P02, but if we would have compressed isentropically for the the diffuser exit, then we would reach the same total temperature, but we would have lower total pressure as P03. So, this is in case of impeller, this is in case of diffuser, and this is for the accelerating nozzle and guide vane. Plus inlet guide vane. It is not compulsory to have inlet guide vane for a centrifugal compressor. So, let us plot the velocity diagram, which is an important discussion point for a centrifugal compressor. So, we will plot velocity diagram. So, in the first instance, we will plot velocity diagram if we have a case where we have this as the impeller, which is rotating in this direction, which is taking air which is in axial direction. So, if we try to plot the velocity triangle in axial plane or the plane containing axis of the shaft, then we have this as CA1, which is axial velocity by which air is entering, but this would be the absolute velocity C1 by which air would be entering, and then this would be V1, and then this all would be U1, where this would remain as CW1, which is the whirl velocity at the intake. So, this is velocity triangle, inlet velocity triangle with inlet guide vanes. Since we have CW1 not equal to 0, but if we consider the same situation without inlet guide vane, then we would have the velocity triangle looking in this fashion. So, we will have CW1 to be 0, and then in that case we have complete velocity which is axial, which is entering, and this is V1 velocity, then and this is U1. Here this is in again inlet velocity triangle, but it is without inlet guide vane. It is also called as without inlet swirl. Inlet guide vane brings in inlet swirl. So, it is since it is without inlet swirl, we have CW1 it is equal to 0. So, this is how air would be entering into the impeller eye, and then while it is leaving, it would leave with a from the tip of the impeller, which has velocity u2, which is tangential velocity, and then since this is a radial kind of situation where air would try to go radially, which is v2 is equal to cr2, and then this induces absolute velocity c2, which has angle alpha 2, where alpha 1 is 90 degree, this is beta 1, this is beta 1 is equal to 90 degree, and this is a special case for radial exit or radial blades. These are called as radial blades. Here we will have axial velocity to be completely converted into radial, and then axial velocity is 0 at the outlet. Having said this, we will move ahead and then decompose the same situation where we are supposed to feel that we are at the impeller I, and then at this inducer of the impeller we will try to plot. This is the inducer of the impeller and this is the complete impeller. So, we will try how the situation is different if we are having IGV and without IGV. So, this is one impeller, this is other impeller. These are the inducers which we are seeing from the front view, and then this is the third impeller. We are plotting inducer of impeller, and they are rotating in this direction. We are seeing from the top, and then in this case we don't have any guide vane, so we are plotting without IGV or without inlet swirl. So, for this case air would enter as V1, then this was the inlet velocity triangle. So, we have CA is equal to CA1 and alpha 1 is equal to 90 degree and beta 1 is actually angle made by the axial velocity with tangential velocity. Here we have CW1 equal to 0. From this figure we can obviously write tan beta 1 is equal to C1 upon U1, or it is also is equal to CA1 upon U1, since we have CA1 is equal to C1 and CW1 is equal to 0. But if we have inlet guide vanes, then the same situation would get differently managed. Here then we have one blade of impeller like this, it is rotating in this fashion. This is again inducer of impeller, and then we have flow coming from the inlet guide vane. So, inlet guide vane is trying to send the flow so we have flow which is approaching in this direction, which is V1 is equal to CA1 for this case, but relatively it is entering like this, where we have this velocity is u1. This velocity can be depicted over here. This is absolute velocity c1, and c1 is making alpha 1. This is beta 1 is equal to 90 degree. So this case is with u1 is equal to cw1, and again we are having inlet guide vanes, but we are making an arrangement where there is no difference between u1 and cw1, since we have u1 is equal to cw1. Having said this, we will mention what are the things related to inlet guide vane. Then due to the inlet guide vane, we have relative velocity approaching the rotor, decreases, as what we can see here. We have inducer and impeller blades as straight, so it is easy to manufacture. So these are the things related to impeller and inlet guide vane. So impeller can be casted, and hence its manufacturing is simple. So these are some facts related to the impeller or inlet guide vanes for the centrifugal compressor. We will move on and then plot for the different case of the centrifugal compressor. Let us say that now the blades are not radial. If the blades are not radial, then they can be backward curved or forward curved. So this is the case where we have backward vanes, and in this case we have velocity triangle at the inlet, which is this v1 velocity, and then we have this as radial velocity, and so this is absolute velocity. So we have CR1, V1, C1. So C1 will make alpha 1 angle. This is complete U1, and then this is CW1. Having said this, this is beta 1 angle. So this is the velocity triangle at the inlet, and at the outlet the velocity triangle will be this way, where this tangentially would go out as V2 velocity. This tangent to the circle will be the tangential velocity, which is U2. So this complete is U2. Then we have this as CR2, and this smaller component of U is CW2, and then this will become C2. So these are the decompositions of velocities for backward vanes centrifugal compressor. Now here we can see that this is beta 2, this is alpha 2, and beta 2 is less than 90 degree, and then this represents the central theme for backward facing vanes, where we have beta 2 less than 90 degree. If we go back and if we see here, then we can see in case of radial we have beta 2 which is 90 degree. So beta 2 remains 90 degree when we are talking about radial vanes. If our vanes are backward facing or backward curved, then beta 2 is less than 90. Having said this, we will go ahead and plot for forward curved vanes, and then we have a different situation where vanes are forward curved. Here again rotation is in this direction, and then curving is also in the same direction. So this is V1 which is tangential in, and then this is C1, and then this is U1. And being the forward curve, this is V2, then we have tangential velocity which is U2, and then we get absolute velocity which is C2, and then in this case this is beta 2, this is alpha 2, and then we have this as forward vanes, and in this case we have beta 2 which is greater than 90 degree. So now for the same inlet velocity triangle we have three options. One is radial, forward curved, and then backward curved. Then we can have three velocity triangles which are possible for the same inlet triangle. So first velocity triangle at the outlet was like this, where this is U2 and then this is V2 for radial, this is C2 for radial. Having said this, this is beta 2 for radial which is 90 degree. Now we will consider the same radial outlet velocity, and then we have three options for the backward sweep, forward sweep, and radial blades. So then for forward sweep we have beta 2 more than 90, so this would be the option for us, where we have this is V2 which is for forward, this is C2 which is for forward, and then this is beta 2 for forward, this is alpha 2 for forward, and earlier case we had this as alpha 2 for radial. Now we know we are talking about the backward swept vanes, and for backward swept vanes beta 2 is less than 90. So this is the option for us. For same U2 we have C2 for backward sweep, we have V2 for backward sweep, and then this small acute angle is beta 2 for backward sweep, and this is alpha 2 for backward sweep. So these are the three options for us for the same inlet velocity triangle and same U2 velocity. Having said this, we will continue, and then we can use the Euler turbine equation, turbomachinery equation, to evaluate the compressor work or stage work. Ws stands for stage, or Wc for compressor. If we have single staging, then the work input is U2 Cw2 minus U1 Cw1. Now let us take a special case where we have no inlet swirl, that is Cw1 is 0. So Wc is equal to Ws is equal to U2 Cw2, and then this can be written as U2 Cw2 can be written. Let us consider the velocity triangle, and from the velocity triangle we can write down it as Cw2 can be written as U2 minus Cr2 cot of beta 2. If we go back and see the velocity triangle, now consider the velocity triangle for the backward facing case. We will draw that velocity triangle. For backward facing case, this is the velocity triangle. For backward facing case, where we have this as V2, this as C2, this will be CR2, this is U2, and then this for us will be CW2. So we want to represent CW2, and so CW2 is U minus this and this X, whatever it is. So this is X is equal to CR2 cot of beta 2, since we know tan beta 2 is equal to CR2 upon X, and this gives us X is equal to CR2 upon tan of beta 2. So X is equal to CR2 cot of beta 2. So you can use CW2 is equal to U2 minus X, and then this X is basically CR2 cot beta 2. Let's define phi as flow coefficient, and this flow coefficient is actually CR divided by U. So we have WC is equal to WS is equal to U2, we can take common, minus CR to U2 into cot beta 2. So we have WC is equal to WS is 1 minus phi 2 into cot beta 2, and in this case we have beta 2 suppose more than equal to 90, suppose equal to 90 degree, that means radial vanes. We have WC is equal to WS equal to U2 square. So let us define one more term, which is pressure coefficient, or loading coefficient, as psi, and then this is WC upon U2 square. So having said this, we will get psi is equal to U2 square into 1 minus phi 2 cot beta 2 divided by U2 square. So flow coefficient, so pressure coefficient or loading coefficient is 1 minus phi 2 into cot beta 2. We can use this for comparing different compressors, which is on centrifugal compressors have different blades, different number of blades, different blade geometries, different pressure rises, different sweep angles, and then if we plot this for a particular case where we have psi versus phi, then we can get a graph which is for beta 2 is equal to 90 degree. This graph is for beta 2 greater than 90 degree, and then this graph is beta 2 less than 90 degree. So this is how flow coefficient would alter the loading coefficient for a centrifugal compressor, and from this we can get and compare different centrifugal compressors. Similarly, as what we said For the work input, we can also say for torque, and we know torque is equal to Cw2 R2 minus Cw1 R1, and for radial vanes torque is equal to Cw1 Cw2 R2. So from here, if we multiply by angular velocity, we were getting the compressor work. Now in case of compressor, or rather centrifugal compressor, we expect the flow to be going out, which is radially. So but it doesn't go, there is a term which is called as slip factor. Here actually air or gas remains reluctant to move along with impeller while leaving the compressor. This reluctancy is what we are talking about, is for the tangential velocity. Hence pressure rise on leading edge of impeller is higher than the trailing edge. Therefore, air or gas does not acquire complete or desired tangential velocity. So in practical sense, Cw2 is less than U2. This is true for radial vanes as well. Hence, we have to define a slip factor, which is defined like this, which is slip factor, and which is ratio of Cw2 divided by U2, and this can be related through a correlation which gives this with number of vanes or number of blades as 1 minus 0.63 pi divided by n, where n is number of vanes, and then we can write down, due to this slip factor there is change in work input, so we can write down Wc, which was earlier said as Cw2U2 minus Cw1U1, where it was expected that for radial case Cw2 is equal to U2, but it is not going to come like this, so we have multiplied by sigma. So for radial case we have sigma U2 square, a special case for radial. So slip factor is going to alter the work input to the compressor. Use of the velocity triangle to find out different performance parameters of the compressor, centrifugal compressor, will be discussed in the next class. Thank you.